Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
So today we're picking up where we left off before spring break, talking about cardinality estimation. And so the paper you guys read today was, I think, a fantastic one from Microsoft, where they go into more deeper into the query plans and try to understand, all right, when the cardinality estimation is wrong, what happens? Not just like, yeah, the query plan gets worse. Why? In what way? And is there a difference between how bad things can get in a row store versus a column store, or some additional query execution optimizations that we'll see in a second? So that's gets sort of a nice follow-up from the German survey paper you guys read. So in the class, I know I still owe every group an email with my feedback from Monday's project proposals, and I owe some of you some data sets and some queries you could use in your implementation. The status update will be on April 7th, on a Monday. So the idea is that on the status update, you come give another 5-minute presentation and say, this is what we've done, this is what's working, this is what's not working. So I encourage you to get started now rather than later. And that way you're not like the day before or the weekend before you have to give a status update. You're like, oh, this shit doesn't work at all. We got to figure out something else. So it's better to figure this out now. Okay? All right, any questions about project 2? All right, cool. For the talks that are coming up, there's a talk tomorrow that's actually in person over in New Simon. This is from QMDB, a company called Layer Zero. This is CMU alum building a blockchain database system. I have strong opinions about blockchain database systems. I think they're a terrible idea or unnecessary, other than the crypto and dealing drugs. But he's going to talk about the system that they've been building. On Monday next week, the creator of Malloy, a query language that's sort of, again, built on top of SQL. That he's at Facebook now, but his company got bought by Google a few years ago. So he's going to give a talk about his query language. And then after that will be the PRQL guys. Again, same thing. It's like another higher level query language on top of Postgres. Yes?
His company was just a new, like SQL, like a new language, and people actually...
Oh, no, so he had a company called Looker that was like, it was like a BI tool. They could automate a bunch of making dashboards, like Tableau kind of thing. And then at the heart of it, they had they had their own DSL, which I'm pretty sure was part of Looker, and then it might have come Looker ML or I forget what exactly it's called. But then I think it got carved off as Malloy as a separate thing. And then he left Google, and he still works on this at Facebook. So that should be a good talk. I thought the Google talk, if you missed it on Monday, was phenomenal. I mean, we can talk a little bit in the semester about why I like that one more so than the German Sane SQL and the other ones. I'm holding judgment yet to say like, oh, which of these projects I think should be the one that we go forward with. We meeting like sort of the database community, but we can wait to see what these other ones look like. Okay. As I said, last class we read this. The journal paper was a survey paper from the Germans in VLDB, where they were trying to measure and understand the effects of cardinality estimation errors inside of Query Optimizer and how that affects the quality of the query plan. And just as a refresher, since it's been a few weeks, remember that the cardinality estimation is the mechanism that the query optimizer is going to use to predict the number of tuples that are going to come out of every single operator in your query plan. Right? And so it's really challenging to do, as we saw a few weeks ago, because you basically have these statistics you derive from the underlying tables, like the histograms or the sketches you've extracted through the analyze process or through when you were bulk loading things. So you have these summarizations or approximations of what the actual data looks like. Then you come along with a bunch of these predicates or expressions. You then try to guesstimate how many tuples are going to come out of that operator from estimating on top of the estimations already that you have from the summarizations, right? So again, it's just sort of errors on top of errors, and the challenge again, reason why we want to be able to do this is because it's good to know, or we need to know how many tuples an operator expects to spit out, because that's going to affect things like join ordering. It's going to affect things like, do we do an index scan or a sequential scan in our query plan? there'll be some other optimizations that we see today from Microsoft. But they didn't invent them, but they use them. Where again, having better cardinality estimations can certainly make a difference. All right. So again, the setup is like we spent the beginning of the semester talking about here's how to actually build a query optimizer, the engine side of things, right? The search process, to do join enumeration, to how you organize the transformation rules and so forth. And then we've always been hand wavy about how we're actually going to cost things. And now we've described at a high level what a cost model looks like, and the core foundation of what the cost model is using to determine the estimated cost of a query plan is going to be these cardinality estimates. And so recall from the Germans paper that they had this nice, pretty graph here, where they're looking at 5 different database systems, and they are just measuring how off the cardinality estimates are for the different operators when you're doing joins, when you increase the number of join operators in your query plan. And as we see, everybody's underestimating, right? Because when we talked about cardinality estimation, we said that there's a bunch of assumptions we're going to make to simplify the problem, right? That all the predicates are basically probabilities that are independent of each other. So you take the probability that a tuple is going to get selected from one predicate, multiply the probability that the tuple is going to get selected in another predicate, right? And that's the total cardinality or total selectivity of a predicate. Of course, that's wrong because oftentimes the attributes have correlations, right? So you can see again the trend where as you add more joins, everybody is underestimating from where you should be or where the actual ground truth is. Right? Nobody's actually overestimating. Again, this is for the join order benchmark, which is a workload that the Germans developed or created for this particular paper, derived from the IMDb dataset. Yes.
Any particular reason why Microsoft is like, as compared to like others, the assumption is like the graph is.
His question is why is Microsoft bounds tighter? Why is it closer to the actual? Because they're doing a combination of the histograms as well as some sampling as well, right? Hyper. I forget what the Hyper is doing sampling. I know Umbra is doing some sampling, but I mean, and so I think it's a combination of better statistics and better estimations upon those statistics, right? So, and then there was this other graph we showed here where they took Postgres and took the join order benchmark, and they actually implemented another cost model that was really simple. It was just like counting the number of tuples coming out of an operator, and that's it's essentially the logical cost of a query plan. And then they compared it against the sort of default cost model you get in Postgres, and one where you actually tune those parameters I talked about before, like what's the relative weight of a sequential scan versus a random I/O, or what's the relative weight of processing a tuple in memory versus processing a tuple from disk, right? And the main takeaway from this, from the Germans' analysis, is that you don't actually need a fancy cost model to get better query plans. It really comes down to, can you have better cardinality estimations, right? So like if you're building a database system or building a query optimizer, you're better off spending your time making your estimations better rather than making a more sophisticated query cost model. So the paper you guys read, they looked at the Germans' work, and they point out 3 deficiencies. Right, they're not, it doesn't invalidate what the Germans had done, because certainly Postgres is acting the way that they saw when they did their experiments. But they felt that the scope of the analysis was limited because they only looked at sort of one workload, join on a benchmark, and they only ran it on Postgres, which I said, I think, multiple times this semester. The query optimizer is terrible, right? And one of the worst ones of the open source systems, despite its popularity. And so they wanted to rectify this by doing a more thorough analysis, similar to what the German paper did, on more workloads and running on SQL Server, right? So the first thing to point out is the join and a benchmark is pretty simplistic queries. There's all this pattern called select project join, SPJ queries. And this is like query 10a from the join and benchmark. But you just see sort of at the top here, we're just a bunch of joins, and then we just have our where clauses are just matching up on foreign keys and primary keys. We have a filter on like a between clause or like a disjunction with a like, right? There is some additional filtering we're doing that isn't just doing the joins, But at the high level, I'm doing a select, I'm doing a project and a join, right? And at the top here, you see I'm doing a bunch of mins. That's just because they don't want to dump out all the results, right? For benchmarking, you just return whatever the min values are, right? So pretty much all the join-ordered benchmarks queries look like this. But as you know, in the real workloads, it isn't always going to be so simple. Not to say it's not common, right? SPJs are super common, but not, it's missing a bunch of other things that people would write in queries. So that's the first limitation. The next one is that they only injected the true cardinality in the query plans for all of the operators in the query plan. Again, the idea is that you have a bunch of operators in your query plan, and the query optimizer, as it traverses that tree or DAG, is going to do lookups in the cost model and say, okay, what's the selectivity estimate for this operator, for this filter, right? And so they hacked up Postgres that allow them to override whatever the estimates are coming out of the Postgres cost model and actually inject the true cardinality. But in this case, in their analysis or their experiments, they're going to do it for all of the operators. And as we'll see in a second from the Microsoft paper, it isn't, you don't actually need to do that for all of them to get the benefits of having accurate cardinality estimations. There's actually a sort of a subset, can be called the essential set, that is like the bare minimum you need, where you inject the cardinality estimation and you get all the benefit as if you injected the cardinality estimates, the true cardinality estimates for all the operators. All right, and the last one that the Microsoft people complain about or bring up is that the paper, again, the German paper only evaluated Postgres in more detail, right? Because it's open source, they can inject cardinalities in that. And there's a bunch of additional optimizations you can do in the actual implementation of your database system related to adaptivity, meaning as the query plan is running, the database system can make decisions actually how to change or permute your query plan on the fly based on the data that it's seeing. Now, we'll spend a whole lecture on this in I think 2 weeks discussing this. The Microsoft one that I'll talk about today is pretty limited. Right? It's just going to change what join operator or what join algorithm you're using. We'll see more sophisticated methods later on. But they're claiming that, okay, in some cases, the data system can actually be implemented in such a way that it doesn't matter if you have bad cardinality estimates, because if you have runtime adaptivity in your query execution engine, then you can overcome these limitations. So again, we'll see that in a second. And Postgres doesn't actually do this. BigQuery is probably the most adaptive of all the OLAP systems. The way they sort of organize their pipelines through this, like always having this explicit shuffle phase that allows them to actually adapt the query plans on the fly, more so than other systems. But we'll see this in a second, or see this in a few weeks. All right, so again, we'll go through the background for the paper, and then again, the Microsoft guys, they broke up the evaluation between the row store and the column store, which I think is fantastic, right? Because again, Postgres is a row store. To do all the findings actually carry over from the row store to a system where you have a column store, where the physical design, the number of choices you have in what indexes you use is much less than in a row store. And then we'll talk about the two additional optimizations they did to do bitmap filtering and adaptive joins. Okay? So I think I already said a lot of this before, but again, the paper you guys read is from 2023. It's a fantastic follow-up from the Germans paper from a few years ago. We're again looking at how cardinality estimation errors affect the query plan quality in a system where you have a state-of-the-art query optimizer. As I said many times, the Microsoft SQL Server 1 is a Cascades implementation. It's very robust. It's very good. And then they also have, I would argue, maybe not a state-of-the-art execution engine. For some things, yes. For other things, no. I would say the Germans' Umbra system is probably better. DuckDB is getting there as well. But I mean, SQL Server has a bunch of other enterprise stuff that big companies who pay a lot of money care about, that like DuckDB is not going to have and Umbra is not going to have. But in terms of like the actual just engine of running queries, I wouldn't say SQL Server is state of the art, right? But it's still very good. It's better than Postgres, right? So again, what they're going to do is they're going to pair. They're going to take query plans in a bunch of different workloads, and they're going to inject the true cardinality estimates and operators for when the SQL Server is using tables or organized tables as a row store, So therefore you have B plus tree, traditional B plus tree indexes. And then when they have these columnar indexes, actually ignore bitmaps. I'll explain what, it's basically dictionary encoding, and I'll explain what they're doing in a second. And then they're going to have this additional experiment, which unfortunately is a bit inconclusive in terms of saying anything direct, like here's how you could actually modify your query optimizer to exploit this. But they determine how to, they start looking at how to identify what's the minimal subset of operators you need to have in a query plan where you can inject the true cardinality estimates or the super accurate estimates and still get the best plan without having to inject it for all your operators. So as I said, SQL Server is using a Cascades optimizer. It's the one you guys read in the textbook from earlier in the semester. And one of the things they talk about, what I think is fantastic, is how they're actually going to inject the cardinality estimates in a Cascades-based system or top-down-based system, right? So what they're going to do is they first generate all the logical expressions for the for a query plan. Right? So you're sort of populating the memo table without doing further exploration or applying additional transformation rules. It's just you just generate, here's all the logical things that exist in my query plan. And then for each logical expression that's in your memo table, they're going to do a recursive hash on that logical expression and all its children expressions and all its children's expressions till you get to the leaf nodes. So now you have this hash that encompasses the subtree rooted at each logical expression in your memo table. And that's going to allow you to uniquely identify it later on when you want to inject the cardinality. Then what they're going to do is take all the logical expressions and you're going to basically do reverse parsing or reverse it back into SQL. And this seems kind of weird, right? Because it isn't always a one-to-one correspondence between what's in a logical expression versus like what's SQL keywords are. But they claim it works. And again, you're going to recursively do this. So the way to think about this is now I have, say I have a select query with a join on two tables. I'm going to have a logical expression that represents the root of that join with all its children going down. Then I'll have separate logical expressions for the outer side and the inner side of the join. And for each of those logical expressions, I'm going to generate a SQL query. So the root will just be the original query we were given, but the children will be like just select star from table foo and select star from table bar without doing the join. And then now I can take all of the SQL queries I've generated, run them for real on the database system, and get the true cardinality measurements for those different operators. And then you store this in a catalog and basically a hash map where you're using the hash you generated from at the beginning. Then at runtime or during optimization time, as Cascades is traversing down and does a lookup to say, to the cost model, what's the cost of this logical expression? It knows and go look up in the catalog and get the pre-computed one that you had before. I mean, it's sort of obvious, but I think I like the way they sort of describe it. And this admittedly, this is the hardest part, how to do this. And they claim that they didn't do it for all the operators. They did for the major ones in the workloads they had to consider. But I imagine this is going to be tricky, as you guys are finding out. All right, so what are the workloads they're looking at? So just like in the Germans, they're going to use the sort of standard cardinality estimation benchmarks. Join in a benchmark. The cardinality estimation benchmark, I think, is an extension of TPC H or DS. Stats is from a data set from Stack Exchange. And then they're going to have the standard industry benchmarks, TPC-DS, TPC-H. DSB is the data science benchmark. This is actually also from Microsoft Research. This is just a modified version of TPC-DS that can allow you to sort of set workload evolution. So like the parameter values can change for the queries over time. So you can adjust skew and other things. And then they're going to have a bunch of workloads that they've collected from both internal applications running at Microsoft and external customers. And then they're going to have a combination of the raw query traces collected from the database system. Like literally, here's the SQL query that I've executed with the exact values of the parameters. And then they're also going to hack up the SQL string, extract out the parameters, and have these sort of templated versions of this. And the key thing to point out, again, why they're doing this complete exhaustive evaluation is because, again, the join order benchmark from the Germans they're using is just all those select project join queries. Whereas for TPC, DS, and H, and DSB, you're going to have the group bys, the outer joins, nested queries, CTEs, and union intersects that make up things you would see in real workloads, right? The real workloads, some of them have some of these elements, not all of them do, all right? But again, it's more things than you would see in the join under benchmark. So the first evaluation they're going to do is run all these different workloads on the row store system. Again, in Microsoft SQL Server, by default, when you call create table, it'll make you a row store system where the tuples are just stored in unorganized heaps, sort of the classic architecture we discuss in 445, 645. You can also do index organized tables where you say, here's the B plus tree, and I store all the data in the leaf nodes. But yet, again, when you call create table, you have to give it extra commands to do that. And I don't think they're doing this for all of them. And then they're also going to create all the expected B plus tree indexes for all synthetic workloads. And then for the customer workloads, they have this tool called DTA. That's basically index advisor for SQL Server that you get when you pay Microsoft money. And so they're going to basically examines the workload, figures out what attributes the queries are accessing all the time, and then has some kind of cost model to figure out, here's the best indexes for me to pick. Oracle and DB2 have similar things, and there's more primitive ones for Postgres and other systems. All right, so the first graph here is going to be the percentage of the queries that are going to change by 2x or more. Like, this is a common thing you're seeing in all the experiments where they really mostly care about, like, am I ever getting 2x better? And the idea there is the 2x is a rough high water mark to say this is actually worth doing, or whatever we're doing to get the more accurate query estimates, it'll make a more of a difference for us if we get at least 2x better query performance. And so the first thing to point out is that in this graph here, the green lines are all the percentage of the queries in each workload that got 2x more or better. The yellow ones are where there is no change, and the red ones is when there's a regression, right? Meaning like you injected, exact, accurate cardinality estimations into the query plan, and then you ended up getting a bad, query plan that's actually worse than you would have if you just used whatever the estimates were from the database system, right? I'll show you also too, for this experiment, all the queries are running as single-threaded, and they're going to disable the adaptive join and the bitmap filtering stuff we'll see later on. So this is like bare bones SQL Server without any additional enhancements. So again, the regressions are rare, although they do occur. And again, it seems counterintuitive that your queries would actually get worse when you have better cardinality estimations. But then again, that's a reflection of the cost model. In some way, the cost model is incorrect, and either through tuning those parameters or just maybe the formulas themselves, and then you end up for some queries getting regression. But it is rare. Next thing to point out is that for this workload here, they actually don't get any benefit at all, right? And for this workload, Real 3, it's basically it's a database system for like a version control system. It's not GitHub. It's probably SharePoint, whatever the Microsoft One Vault or Perforce. They have some other one that's not Git that has sort of been relegated. But think it's something like that, right? Like it's the GitHub catalog. And for this one, for whatever reason, the queries are not getting any major better. Again, it doesn't mean that some queries aren't getting some improvement. Like if you look over here, there is a minor bump, but the percentage of queries that are getting 2x faster is actually low. So again, then we have these guys here where TPCDS and the real workload for the templated version of it, that's what the instances is what the INST means. For these ones, you're getting a overall reduction in performance. And the main takeaway from this one is that a majority of the queries are actually getting faster, but for the queries that are actually getting slower are having regressions. The absolute time of their regression is so significant that it negates any of the benefits you're getting from more accurate cardinality estimations, right? So most of the queries are getting faster, right? You can see there's much queries here getting 2x faster, but the ones that are getting slower are, the absolute numbers are quite significant. And again, this is a row store running TPCDS. TPCDS is a lot of joins and a lot of CTEs. So it's pretty nasty. It surprises me that you don't see the same effect in DSB, because TPCDS DSP is derived from TPCDS. I think they simplified it a little bit, but still, to me, that was surprising. All right, so now we see, again, so we're seeing some benefit and we're seeing some reduction. The question is, all right, what's actually going on? Rather than just looking at these core screen results, right, it doesn't really tell us what the optimizer is actually doing that's, with these better cardinality estimates to make things run faster. So this is where they are actually going to do a drill down or do inspections of the query plans that are generated from the previous graphs and try to understand why the query plans are actually getting faster. Like what changes in the query plan itself from the original version to the newer version with the more accurate cardinality estimates that's causing them to get better performance, right? And as they point out, and the Germans also point out too, it isn't just because now we have better cardinality estimates that we're going to generate better join orderings. In the case of Postgres, the Germans point out that when you have better cardinality estimates, you end up doing less index scans or index seeks. And because basically, if you're underestimating how much data you're going to get out from a table, right? If you think you're going to get 5 tuples instead of you get 5 million tuples, if you don't think you're going to get 5 tuples, then you're going to choose an index scan. But then it's only when you start then scanning that index you realize, oh shoot, I was wrong, and you're getting way more. You're getting more tuples than you expect, and an index scan is be always way more expensive than a sequential scan if you're reading a lot of data. So what they're going to do is for all the queries where you got 2x better, they're going to categorize them and, based on which class of operators within the query plan are going to generate 50% or more of the improvement, the overall improvement that they're seeing. So the first category is going to be seek operators or index scans, right? So these are if you're accessing a base table with an index and you're doing basically random I/O, so index probes, index scans, right? That would be the first category. Scan operators would be sequential scans if you're just scanning the blocks in a table from beginning to end. Non-leaf operators would be everything above the leaf nodes in the query plan, so aggregations, sorting, limits, whatever else you have, joins. And then miscellaneous or catch-all is their term to say for the operators that don't fit into all these other stuff, a bunch of random things. And they put them into this. So this chart here is showing the percentage of the queries for each of these benchmarks where you got a 2x improvement and categorized based on which of those 4 categories from before, like which of the operators are generating the most benefit for the system, or for the query, when you inject it with the better statistics, right? And the first thing to point out is for the cardinality estimation benchmarks in so job, stats, and CEB, and for these workloads, determining whether you actually want to do an index scan or not makes the biggest difference, right? It's a pretty sizable percentage of the queries, over 60%, are getting the benefit because of this, because you're choosing not to do a index scan and instead you're doing a sequential scan. For all the other ones, it's the combination of the other 3, right? There isn't one that dominates. Like in this one here, it looks like the scan makes most difference. Scan and the non-leaf ones are sort of about the same there. But for the real workloads, it's basically almost split even between these three things, right? So again, in this case here, again, this is just saying that in the Germans' paper, they would have solved this. They would have solved that if you figure out that you don't need to do index scans and get Postgres to do sequential scans, either because you identify that the access method or the scanning that table is going to produce a lot more tuples than you think it's going to produce, and therefore you don't want to use the index. Or in some cases, if you reorder the joins, you end up not needing to do an index probe. You get a huge benefit. But for all the other workloads, it's actually all of the above, right? All right, so let's go more detail and understand what SQL Server is actually doing, how it's actually modifying the query plans for 2 of those categories when it has better cardinality estimates. So for this one, we're going to do in the join order benchmark query 17a, and as I said, it basically looks like this: a bunch of joins, a bunch of predicates that you join the tables together. There's a like, there's another keyword lookup there, and then we're just getting the min values, so we don't get all the output of the query. So here's what the original query looks like when it comes out of SQL Server. When you let SQL Server use the cardinality estimates that it generates when it ran analyze on its own, right? And the way to understand this is that the sort of the white guys here and then the pink ones here, these are all the query plan operators. The gray boxes here are the cardinality estimates with the estimated selectivity or estimated cardinality of each of these operators generated from the derived statistics, and then the actual is the one that it saw when it actually ran. And then the dotted lines here just correspond to them shortening the query so they don't have the full query plan. So they're sort of cutting off, saying there's something in between here, but we don't need to show because it's not relevant to the example. Right? In this case here, there's 1, 2, 3, 4. There's 4 joins, but as I showed here, we're joining way more than 4 tables in the query. All right, so if we inject now the true cardinality estimates in the query plan, right, using that method where they're hashing it and injecting it into the system catalog and the query optimizer, right, this is what changes for this particular query. So the first thing to point out is that we had this seek operator. So CI is clustered index on this table here, and this changed now to a clustered index scan, right? Because if you look up above, the cardinality estimate told us that we were going to get 1 tuple out of this. In actuality, we got 300,000. So now with those accurate statistics, it recognizes that, well, I don't want to do an index probe because I'm not going to get 1 tuple. I'm going to get a bunch of tuples. And then I actually want to put this on the outer side of the join instead of the inner side, right? And actually, also in the case here, you can see that it switched from an index and nested loop join to a merge join, right? Because the index scan is going to give you the data in sorted order. So again, now you see, again, by injecting the true cardinality estimates, we have a better sense of like what access method or what scan operator we actually want to do on this table, and then where to put it in the join. The next one we have is this one here, where we're doing an index seek on the cast info table. And again, the cardinality estimator said, okay, you're going to get 15 tuples. In actuality, you got 2.8 million. All right, so that's pretty off. And so by switching over here now, I actually don't know why this is like this, right? Because it says it's estimated 24, but you're getting back 1 million. So I think that's a mistake on their side, just in the diagram. But again, the main takeaway is that it's still an index seek, but we changed what it's joining against, right? So it was joining against what was coming out of this thing here, and now it's joining against what's coming out of this hash join here. All right, and the last big change to point out here is going from this index nested loop join into this hash join. The join order still stays the same, right? We do keyword on the outer side and the movie keyword on the inner side. We see the same thing for the updated query plan. But the main idea here is that on the probe side of the inner side of the join, we thought we were going to get 33 tuples. We actually got 41,000. And then when we switch now from an index scan to a clustered index scan, just scanning along the leaf nodes, right? Yeah, we're gonna scan the 4.5 million, all 4.5 million tuples of this table, but we know that I don't know why they're actually doing a hash join for 1 tuple, but I mean, an easy way to do that is just like if my key equals your key, admit it. You don't need to build a hash table for that for 1 tuple, but whatever. So anyway, so they're scanning along and they're probing this thing, and then obviously this is going to be way cheaper than having to do multiple probes into the index. So that's what's going on. So SQL Server now with better statistics is able to switch when it's doing an index seek into either a sequential scan, doing index probe or index seek to either a sequential scan or an index scan on a clustered index. And that's, again, why this query is getting faster. The next one they make a big deal about as well is to do aggregation pushdown. And this is one of the optimizations that they say that Postgres can't do this. I know Snowflake can do this, BigQuery can do this, a bunch of other systems can do this. Postgres cannot. I don't know, DuckDB probably can do this. I haven't tested. And so here we see that we have a join, doing a hash join up above, and then we're going to take the output of this hash join, we're going to sort it, and then do a streaming aggregation, which is basically a sorted aggregation, right? So with now true cardinality estimations, what happens is that you end up moving down or breaking the stream aggregation at the top into a hash aggregation where you build a hash table and maintain the aggregation as you're going along. But then you still keep the streaming aggregation up above because you still need to sort of finally clean things up at the end to get the true cardinality or true aggregation out of it. And so what you can see what's happening is that over here, we thought we were going to get 96,000 tuples coming out of this hash join, but in actuality, we got 5.8, right? So we're way underestimating or SQL Server is way underestimating the number of tuples that are going to get qualified for this join predicate here. But then now, if we, with the true statistics, we would recognize, all right, well, the number of tuples that I'm going to condense this down into up above when I do my aggregation, I'm going to go from 5.8 million to, what is that, 41,000. So in that case here, I'm doing a bunch of join matches in my hash join here that for tuples that is going to get coalesced and combined together, aggregated together up above in the query plan. So what you're better off doing is actually computing the partial aggregation below the join, which we talked about before. We talked about transformations. And then now when I do my join, my hash join here, I'm joining against my hash aggregation, which is 41,000 tuples, rather than the 5 million tuples I would have if I didn't aggregate beforehand. Right? So that's why for this one here, this is a huge win. And basically, you can see how the I don't know why they still keep the stream aggregation, because after you sort it, we have to look at this is for the real workloads. We don't have the real query, but like maybe there's an order by where you have to sort it at the end. But in actuality, if you know that you're not doing any filtering or aggregation coming out of this hash join, you may not actually need the sort or the additional aggregation up above. But then there might be an order by or limit or something else above in the query plan where you have to do this, so they have to keep it. Actually, yeah, you can see that the dotted line here means there's something up above that we don't have here. So Snowflake can do this. All right, Snowflake basically puts we'll talk about adaptivity later, but like they put the hash aggregation in there in the query plan always when you have sort of a pattern like this, and then at runtime they can decide whether to turn it on or not based on how much data is coming out the leaf nodes below you. In the case of SQL Server, they can't do that. They always put it in there, but the idea is basically the same. Okay. So what's going on? Why are these cardinality estimation errors? Like we've seen how they manifest or how they affect the query plans when they're accurate, but why is this occurring? And so in this paper, which corresponds with or corroborates what the German said, is that when you have skewed data, especially when you're doing joins on skewed data, then your cardinality estimations are just going to underpredict or overpredict the number of tuples that are going to come out of that join, right? And then again, the errors of a join cardinality estimation is multiplicative because it sort of rides up to the query plan. Now you have bad estimates from this join operator being fed into another join operator that's going to generate more bad estimates. And then things get worse, as we saw in that graph from the Germans earlier, right? The other challenge they also talk about is that when there's skew, you end up, and you have filters, you end up just incorrectly predicting the number of tuples are going to get filtered out by your predicates. And it's basically the same thing as the join skew. All right, so before I talk about the Columnstore evaluation, I want to briefly mention what the SQL Server Columnstore extension or it's not really extension because it's built in, but what they're actually doing, what is its capability? So if you remember your database history, column stores became a big thing in the mid to late 2000s, 2008, 2007, right? Systems like Vertica, Greenplum sort of came around the time. I think Park-Cell, which then became Redshift, but at the time they were originally a row store. But there was a couple other column store systems that were around. And it became clear that if you're doing analytics, you want to run on a column store system. VectorWise is probably the other famous one as well. And so in 2010, early 2010s, Microsoft announced and released a new feature in SQL Server that allow them to do compressed Columnstore indexes. So the original version of this was what's called a fractured mirror architecture, which was invented by Jignesh Patel's PhD advisor back in Wisconsin, David DeWitt. The basic idea is that you have your row store, all your updates go into the row store, and then there's like a background job that takes the updates to the row store and then converts the tables into a column store. And you do this sort of incrementally. Oracle basically, their in-memory column store basically works the same way, right? And then a query shows up, the system can then figure out, do I run on the column store or the row store, depending on what data I actually need, right? But then later on in, I think, 2016, SQL Server then added the ability to not have the row store at all and to say that this table is going to be stored as in these column store indexes. So then they had to add support for insert, update, deletes, and you basically add this delta store, think of it like almost like LSM, where all your modifications go into the row store space, and then just like before in the background, there's a job that goes ahead and compacts it and then builds the columnar data. It came out in 2014, and then I think this came out in 2016, but whatever. So basically what they're doing is that, assuming you have your data table looks like this, they're going to break this up into row groups, similar to what we saw in Parquet and Orc and other things. I think it's 1 million tuples. And then for each of the columns, the attributes in the table that you care about within each row group, you're going to build basically a columnar data representation. So you're going to encode and compress it, and you're going to store it as basically a bunch of contiguous data as columns that are all dictionary compressed. Right? I think they can do also RLE and delta encoding, like all the tricks and compression stuff that we talked about in the intro class, or if you take in 721, all those tricks they're doing here as well. And what's interesting about it is that they didn't actually have to make major changes in SQL Server to store all this. They're just storing this as blobs, right? As the regular blob store that no one uses for tables. It's just that when you get back a chunk of data, out of the blob store, you have an execution engine that knows how to interpret it as columns. Yes.
So it's like the Microsoft, like one table can be as a row store, stored as a row store, and one table can be stored as a column store. Can it just as like a hybrid architecture? And then let's say if you do joins in that, won't that affect like the assumptions that we make in general that is going to have this much of like performance or etc. Can it change?
So the statement is that in SQL Server, when you create a table, you can specify I want it to be a row store or it can be a column store. Yes. Also, you can have the row store and you can say, but also build me column store indexes on it. But the primary data or the data of record is going to be in the row store, right? So you can do that. Then your next question is, all right, well, now if you have a bunch of mixed table types where you have a bunch of row stores data and you join against my column store data, isn't that going to be slow? Yeah. Yes, probably, right? Because at the end of the day, if you have really wide tables in your row store and you only need one column at it, who cares whether you have a fast vectorized engine? You still have to read entire pages just to get one column. Yes. So Microsoft will say, don't do that, right? Or keep your row store, but then still build the column store indexes on them, because then you can do joins on the column store indexes, right? And they're happy to charge you money for it. Okay. So I think I've already said this, but as part of the changes of adding column store indexes, the columnar storage in SQL Server, they modified the query optimizer in SQL Server to now be aware that there's columnar indexes. And they actually didn't make major changes to their Cascades implementation because it's just another access method. It has a cost like any other access method, right? It's no different than if I add a new index type, like a hash table or a try or something like that. It's basically the same thing. And now you can, within your cost model, you can account for the performance benefits that you get if you choose a columnar storage versus a row store. The other thing also point out too, which is sort of related to his question, is the original implementation of SQL Server, which is based on Sybase from the 1980s, even though they rewrote a lot of it in the 1990s, is a row-oriented system that's doing the Volcano query processing model. So they're calling get next and getting one tuple at a time. But then obviously that's going to be terrible for your columnar storage, right? Because now you have all this columnar data, and if you're still getting the data out as putting it into a row store engine, like I said before, you're not going to get all the benefit. I'm pretty sure Microsoft bought this distributed version of Postgres called Citus out of Turkey they had their own Columnstore extension called CStore. I'm pretty sure in that system with that extension, you still got, like, even though it was a columnar data, you still got the data out as rows, and you ran it through Postgres's row query engine, which is going to be slow, right? There's a bunch of other extensions people are trying to work on to add column stores in Postgres. The ones that are probably most interesting is where you circumvent the row store column or the row-based execution engine Postgres and let it run like DuckDB or ClickHouse, because then you're getting all the benefit of a columnar vectorized engine. All right, so again, that's the basic idea, is that there's the data system, the optimizer is aware what the physical layout or design of every single table. It can now make decisions on the appropriate way to access them. So for their column store evaluation, they're going to store all the data within the columnar storage in SQL Server. So they're not going to do the row store, they're not going to do the fraction mirrors, and there's not going to be any B plus tree indexes. It's just going to be those compressed dictionary columns that we talked about before, right? And so the overall improvement is roughly the same for most of the workloads. There are some outliers that we'll go through, but in general, the main takeaway that they found is that having better cardinality estimations for a column store system is equally as beneficial as you would have in a row store system, right? And again, in this environment, the index scans are rare, so you're not getting a lot of the benefit you saw in the row store system where you say, okay, this should be not index scan, it should be a sequential scan. Most of the times you're just doing a sequential scan, but on the compressed columns. So the first thing to point out also too is that the speed up is roughly the same, although CEB is quite significant here. But there's a larger number of queries that have regressions in these different workloads. And the overall regressions you see for the total elapsed runtime of all the queries is much greater. And again, what they point out here is that it's not that overall you're getting worse query plans in your column store than you would in the row store. It's just the ones that do go wrong, the absolute numbers or the absolute degradation in their runtime is so significant that it negates any benefit you're getting from other stuff. Right? In the case of Real 1, right, there's a large percentage of over 20% of the queries are getting at least 2x faster, but the overall runtime is reduced because for the ones that got slower, they're dominating the total runtime.
Any particular reason for like TPCDS?
Statement, the question is why is TPCDS the worst one here? I forget. I have to go look.
I mean, the general point is that the worst queries are really bad.
Yeah.
So they're just making it look really bad.
But in the row store, I think evaluation was not as bad as it was.
Not really talk specifically about it.
So this is all like percentage, right? So the row store is definitely way slower for TPCDS, right? And so like does it mean now your query is going from 10 hours to 9 hours, whereas in this case here it might be going from 10 minutes to like 20 minutes, right? So it's 2x worse, but like the absolute time is much less. All right, so the next experiment they did, which I think is phenomenal, although it was very short and brief, they talk about additional things they want to do, is they asked the question, okay, well, most of the time, excuse me, you're going to get a benefit if you inject true cardinality estimates into your query plan. But in the case of the Germans and the experiments we've seen so far from Microsoft, they're injecting the true cardinality estimates for all of the operators in the query plan. And so the question is there a minimal subset of those operators in each query plan where if you only inject the cardinality estimates for just those operators, you still end up with the best plan you would get if you injected the true cardinality estimates for all the operators, right? Because again, getting the true cardinality estimates is super expensive, right? These data sets are kind of small, but think of like if I have 10 petabytes of data and I have 1,000 tables that I may be accessing in my query, I don't want to have to do a sequential scan on every single one of those tables just to get the true cardinality estimates and then inject it in the query plan and get the best result. So is there a way to identify what's the minimum subset that we actually need? So they're going to identify that the groups within a query plan are considered the essential subset if you inject the true cardinality estimates for those operators, you end up with the same query plan you get if you do it for all of them. And that if you remove any operator from this minimal set, then the query plan actually gets worse. And what's fascinating, they don't go too much detail about it, is that there's different ways to explore like what the minimal set is. Because in some cases, if you remove one operator from the essential set first versus another one, you may end up making the query plan worse. But if you remove one versus another, if you switch the order in which you remove them, you may end up with the correct results, or is it the best plan, right? So they're doing basically brute force search to calculate this, which is, again, super expensive. You wouldn't actually do this. It's not practical in a real system, but it is interesting to see that, again, there is actually an easier way to do to inject the better cardinality estimates to get the better query plans without having to do for all of them. So this scatter plot here is where along the x-axis is the total number of groups, they call them memo groups, but the total number of the logical groups in a memo table for each query plan. And then the y-axis is the number of groups that are in that essential set. And so the main takeaway is that for all the queries, the median size of the essential set is 5. There's one outlier where if you have 1,000 memo groups, the essential set is like almost 100, right? And you think of those as like accessing a base table, but 5 is actually practical, right? And maybe again, you can think of now in your database system, you can then prioritize running analyze, or as you're inserting new data, you spend a little more work for those tables that maybe actually matter the most. Although it's not based on table, it's actually based on the operator. So what table matters the most from one query to the next may change. But they haven't, I think they said there is some overlap, but they haven't done a full evaluation of this. So I think this is super fascinating. It shows that you don't have to do the exhaustive injection of the completely accurate statistics that the Germans did, and you can still get some of the benefit. As they talk about in the paper, further studies needed to understand this. Yes.
What were the studies?
So they were saying, like, they talk about how, again, the way you calculate the essential set is very inefficient with what they're doing now, and that the ordering in which you remove things, because they're just putting them all in and removing them one by one. They're doing brute force search. So is there a better way to do that?
But what's the value of doing that? Like, the point of this, at least, was the takeaway is that, hey, if you, like, there are some important ones, and as long as you get it right for those important ones,
yes,
you're fine.
Yes, but how do you identify the important ones? That they're saying that's super hard. Furthermore, they're also doing exact cardinality injections in this. And so if you have now the essential set, assuming you have a magic wand to calculate that, do you have to have, how off can your cardinality estimates that you're injecting actually be and still be okay?
I see.
Right, so there's a bunch of different questions about how to handle this.
What can be the approaches? Like, I mean, are they exploring anything like some weightage they would keep on certain things so that they can search for that a better way? Except for like brute force, like what are the ways that they can get a better way of like searching things?
So his question is, other than brute force search, what they're doing now, what would be a better way of doing this? Again, if you can retain from one query plan to the next, what was that essential set? And there's a way to categorize or classify why, or understand why those operators are part of the essential set. And therefore, like if there's something about them, like they're accessing a super wide table or a really big table, or like if there's something about a given operator that causes it to have a pronounced influence on the quality of the query plan, if you can identify that, within a query, now when a new query shows up, you don't have to do the brute force search. You can rely on that history you had before.
So, but it will be like a bunch of like fixed set rules. Like, okay, this thing may be like.
Nobody knows. They don't know. All right. Again, like I got excited when I saw it. Like, when I read the paper, like, they're going to do this. And when I got to the section, it's only like 3 or 4 paragraphs, right? Again, I'm not diminishing the results. It's just, it wasn't the main focus of this paper, but it shows again that like this does make a difference, and this is something worth pursuing, and maybe they already are. The way to understand industry papers, although Google is certainly like this, Microsoft is pretty good about putting stuff out in a timely manner. But oftentimes, like whatever the paper you may be reading from a company, like it's already out of date internally. Like they've already filed patents on it, and it's already been like out for 5 years. Like when the Spanner paper came out in 2011, Spanner's been around for like 4 or 5 years. That's what Jeff Dean said, right? Like, but they wrote the paper, wrote the patents, and then it came out, right? And then they moved on to the next thing. For Microsoft, because this paper's coming out of Microsoft Research, this I like to think this is pretty bleeding edge. They're still going to file patents on it because that's how they do promotions at Microsoft and a lot of companies. And it may be the case that they didn't actually. There's nothing that they've implemented in this paper we read that's going to be in SQL Server, but certainly it's going to provide guidance to the SQL Server team about things they could potentially add on. So I'm trying to say that this is. I don't know whether they've taken this paper and they have a better version of it. I think this paper is 2023. It's still pretty up to date, but they haven't announced anything. Hey, this new version of SQL Server can take advantage of this. And again, who knows whether Oracle and other companies are doing this? They just don't talk about it. All right, so as I said in the beginning, the SQL Server has 2 additional optimizations they can do where the question is, for a Columnstore system, if you can do these additional runtime optimizations, is that going to mask the problems you have when you have inaccurate cardinality estimations, right? So again, the idea is that it's so expensive to get the true cardinality estimations, whether or not you're doing the essential subset or not. Then do you actually even need it if you can do these 2 additional optimizations? And I will say these are not unique to SQL Server. This first one here, the Bloom filter stuff, that's pretty common. Most OLAP systems do this. The adaptive join one, I think, is specific to Microsoft, but I don't say it's weak, but it's pretty tame compared to the other additivity stuff we'll see later on. So this is just a reminder of what we're talking about from 721 or 445, 645. But the idea of what they call bitmap filtering is what we've called sideways information passing in other lectures. The basic idea is that if I'm doing a hash join, as I'm building the hash table on the probe side, the build side of the join, I'm populating the hash table with all the keys, do my join. I'm also going to build a Bloom filter. I populate that with the join keys that I'm populating my hash table. Then now on the probe side, I pass along the Bloom filter so that as I'm scanning along and generating tuples to go up into the join, I first check the Bloom filter first. If there's a match, then I check the hash table. If there's not a match, again, Bloom filters can have false positives but not false negatives. So if there's no match, I know it can't be in the hash table, so then I don't have to do the more expensive probe in the hash table. The Microsoft one is a bit more complicated because they can generate all the Bloom filters for all the joins ahead of time and then try to push that down into the leaf nodes and try to filter things super early. But the basic idea is the same. So the question is going to be, okay, well, if we can do this now, for really selective joins, where most of the things are going to get thrown out in my Bloom filter, does the cardinality estimations actually matter? Because now I can hide the stupidity of my query planner having the wrong join order and doing wasteful things because the Bloom filter stuff is just filtering it all out, right? So this only works on the this is only going to work if you do a hash join. If you're doing other joins, you can't do this. But most OLAP queries, most of the times you're doing hash joins, right? I think the vector-wise guys probably invented this, but earlier in 2007, the vector-wise guys say that they got a 2x improvement when they do this. The Germans and Umbra, they said they only get, it only helps for a small number of use cases, whereas the vector-wise guys say that this matters a lot, but that's a separate topic for this. All right, so there's 2 graphs here. The first one's going to be when you have the estimated cardinalities generated from the database system itself, and then the other one's going to be when we have exact cardinalities. So this one here, they're enabling the bitmap filtering for both these cases, and then the baseline comparison is when you have the estimated cardinalities from the database system and without the bitmap filtering turned on. So bitmap filtering is turned on for both these graphs. This is with the estimated cardinalities, and the other one's with the exact cardinalities. And so by just enabling the bitmap filtering without any super accurate cardinality estimates, about 36% of the queries are going to get 2x or more improvement in performance, right? And there's almost no regressions for this because the cost of building the Bloom filter is pretty cheap, certainly relative to the hash table, and probing it is super cheap, again, relative to the hash table. So there's kind of like, there's basically no downside of turning on the Bloom filter stuff, regardless of what your statistics look like. There is a excuse me, a minor improvement if you have true cardinality estimates, and you're still doing bitmap filtering. And again, this is because now in some cases where you can get the join order in the right way, you just end up filtering out things sooner than you would when you have bushy plans, which I think is what's going on here. But again, it's not a major improvement. This is basically saying like the bitmap filtering, the Bloom filter stuff, that's going to get a pretty big win even without good cardinality estimates. But it does mask a little bit of the inaccuracies. All right, the next optimization we're going to do is what they call adaptive joins. I think they added this in 2017 in SQL Server. And the basic idea is that you have a special physical operator called an adaptive join that basically has a flag inside it that tells you what join algorithm you're going to use. And it's either a nest loop join or a hash join. Right? You can't do merge join because you need to have the database in the right sort of order coming up. So what happens is that any place you're going to do a join in your query plan, you just insert one of these adaptive joins. And then there's a threshold you set as sort of the administrator that says, if now on the outer side, if I see more tuples than above some watermark, I'm going to switch from the nested loop join to a hash join. And you basically throw away your results that you've done so far, right? Because again, the threshold I think is like 100 tuples. It's pretty small. And then you just stop probing on the inner side and just go back and rebuild the hash table, right? So the idea is, again, I have this predicate here. Say I underestimate the number of tuples that are going to come out of it, and I'm actually going to get way more than I have. Again, at runtime, I just flip this to be a hash join, go back, start my iterator over on the build side, build my hash table, and then just do the join as before. Yes?
But isn't it pipeline? It's like you have to store what S has been sending you for so long while you're doing the solution, right? Like you need to store the things that are coming out on the right side somewhere. If you want to be able to switch. His
statement is, do I need to store what S is sending me?
Yes.
No, I haven't got there yet. You can only do it on the outer side.
I see.
So I call get next 10 times or 100 times,
Right.
and then too much, right?
Yeah.
That you can easily buffer, like whatever,
Yeah.
right?
So like reset the entire thing and start from the beginning, or is it like it stay from the point, like it start from the point where it has stopped, like the previous execution?
This question is, how far down do I have to restart? Again, it's the threshold is pretty low, right? I don't know what the batch size is in SQL Server, but like on DuckDB, it's like 1024. I mean, for each get next call, I'm getting 1,000 tuples. So if I'm getting 1,000 tuples from down below me, that's easily above my threshold of 100. So I don't even bother doing the hash or the nest loop. I just switch over to the nest loop join. But it's pretty, the watermark is by default super low because you don't want to have to go back and rescan a bunch of stuff. Yes?
Is the adaptive join a special operator, or they just the database checking the hash join, like, or nested loop join at the runtime, then swap into? Because if it's a special operator, but the cost of hash join and nested loop join are widely different, then how would the cost model like choose the corrective plan?
So the question is, before you actually run this, what does this actually look like in the query plan? Is it an explicit adaptive join operator with a flag that says it's nested loop join versus hash join that gets toggled at runtime? Or is it just a nested loop operator, join operator, which I could then cost as if it was any other operator, right? My understanding is that it's a special operator, and by default, it'll get costed. You only do this if you assume you're going to get not a lot of tuples, and therefore you're going to be a nested loop join. Obviously, if you know you're going to get a lot, don't even bother with this and just do a hash join. So it's for corner cases. So the default cost is going to be the nested loop join. But at runtime, it may switch. And again, all they're doing is changing the join algorithm. They're not swapping R with an S. They're not doing any of that stuff. We'll see that later. Basically, the reason why it's quite limited is because, related to his question, is if I make a major change in my query plan, I got to throw a bunch of results away and start recomputing it. And most people don't want to do that. In the adaptivity stuff we'll see later on, they're basically going to have like triggers in the query plan they insert so that at runtime, if you see, it's basically the same idea. I'm getting way more tuples than I actually expect. And in some cases, they can change what the query plan looks like up above. You keep what you've computed down below, but you change up above. In other cases, you say, we're way off here, throw away everything, go back to the optimizer and generate a new query plan. Well, again, we'll see that later on. All right, so this graph is not really surprising. Basically, it says like for the estimated cardinalities, just doing an adaptive join, you're not getting a huge benefit, right? Because again, this is basically what his question was. I'm costing it on a nested loop join, and in some cases, that's going to have effects in the rest of my query plan where I may be choosing indexes that I shouldn't be choosing. I may be choosing join orders I shouldn't be choosing. So even though I can adaptively change what join algorithm I'm using, I'm still going to have a potentially inefficient query plan. Whereas if, again, I have the exact cardinality estimates, right, I'm seeing more greens on this side here because, again, now the optimizer can make better predictions. Right. Again, the excuse me, is only optimizing joins. It's not optimizing if we do join orders, what access methods we're doing, aggregation pushdown. So all the other optimizations we saw when we have exact cardinality estimations, you can't do with this adaptive joining thing. All right, to finish up, so again, the main takeaways of this paper is that having true cardinality estimates are going to have a similar benefit to column stores as it does row stores. Again, for all the reasons that we talked about throughout today's lecture. There will be a small percentage of queries that are going to have regressions. And you think, okay, well, maybe like they said 1% or less. Maybe that's not big of a deal, but certainly we saw in the total, in the column store graphs, those regressions were pretty significant in terms of absolute time. And if you're at a company or organization that has a DBA, DBAs are super conservative and super paranoid because if you now upgrade your system or you add, you inject new cardinality estimates or something like that, and now you have, 99% of the queries are running faster, but the 1% of the queries are running slower, who do you think is going to call you and complain that the queries are running slower? It's that 1%, right? And so oftentimes DBAs don't like upgrading, don't like making major changes to their systems, database systems, because they don't. These regressions are bad, right? Like it may be like the one query that gets slower is like the CEO or CTO's query, and they're calling you at midnight complaining why is my database running slow. Again, there's ways to get around this. We'll see this when we talk about parameterized query optimization. But basically, you can, and this is sort of how they did the cardinality injection. In the enterprise systems like SQL Server and Oracle, you can extract out the query plan as like an XML file or JSON or YAML, whatever you want, and then now you can then load that back in, and no matter how the query optimizer changes or what stats change, it's always going to use that exact same query plan where you're always going to have consistent performance. It may not be the best plan, but it doesn't make things run slower, so nobody complains. Right? There's sort of management ways to handle that. So those are the kind of things I keep bringing up, like enterprise stuff versus like Postgres and DuckDB and SQLite. Like that's things enterprises need to have, like plan management and prepared statements. And well, Postgres has prepared statements, but like doesn't have a way to inject and query plans and maintain a catalog of these things. This is what the enterprise guys do that the open source guys don't. And then as we saw in the for the essential set of operators or logical expressions. It's only about 5% of them at most are going to be the ones that we need to have super accurate statistics in order to get the best query plan, which is, I think, achievable. Okay? Any final questions about today's paper? So next class, we're going to bring up, we'll discuss, I think either one of you guys in the front brought up, like, hey, this seems like this be a ripe for using machine learning, because what are you doing? You're trying to learn distributions on data where you have a history of things and you can observe what happens. So this would be the first lecture we're going to discuss, or paper we're going to discuss about using machine learning inside of Query Optimizer. I will say that there's a lot of papers in this space. Cardinality estimation is the prime target for this, because again, histograms and sketches and things like that are error prone. It's used selectively in commercial systems. They don't publicly talk about it, right? So Postgres is not doing this ML stuff. SQL Server does a little bit. Redshift does a little bit, but a lot of it isn't public what they're doing. But no one's going to do like the full-blown replace your histograms entirely with ML models. Nobody does that, and we'll see why. Okay?
We're gonna go with Brownie. Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Get one, Big Al, Mike Strokes, Drumley, I'm not the one who be yapping up the weak ass rhymes. If you to spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like a make them hoes fuck quick and suck dick. Crown me as the thugs in the gun. Shit, some niggas claiming that the rapping is sudden. Don't push the button, yes you motherfuckers in front.